Hey everybody, welcome to Enthalpy, Entropy, and Spontaneity. So here's video notes 9.1. Here's the 3 things we're going to be able to do, hopefully, from this video. Read section 10.10 in the book. It's a couple of pages, and then write down 3 questions. 3 questions. Let me go back. 3 questions. Let's get that here. 3 questions. 3 of them. Okay. So spontaneous reactions. A reaction is spontaneous if it proceeds on its own without outside intervention. It has naturally favorable conditions at some temperatures. So spontaneous reaction means without outside intervention. It goes. It just goes. That's what spontaneous means. It goes. So here's some examples. Iron rusting. That's spontaneous. Hey, it looks like neighbor. Melting of ice. That's spontaneous. You put it outside. Hey, it's going to melt. Not at every temperature, though. So let's talk about what spontaneous doesn't mean, because sometimes this is what people think. So spontaneous does not necessarily mean rapid. Okay, we are just done talking about rates of reaction. So we can do slow or fast spontaneous reactions. It doesn't mean explosive. It may or may not be explosive. All right, so we're not talking about the rate of reaction, just will it go or will it not go? That's what spontaneous means. So outside intervention. Some spontaneous reactions require an initial spark, but they're still considered spontaneous because you got to activate them. Okay, so the initial spark is activation. Well, it's hard to see. Activation. All right, but they go. Like once you start a fire, it's going. I mean, if it runs out of fuel, it's going to stop, but it's going. You might have to spark it, but then it's going to go. All right. Non-spontaneous reactions also can occur, but what the heck is going to happen to them? You have to add outside energy to make them go. All right. It's not a naturally occurring thing. You get it to go, you have to keep adding energy into it to keep it going. All right. That's not what a spontaneous one does. Once spontaneous is going, it's going. Right? Not spontaneous is like skiing uphill. Not spontaneous, like skiing uphill. Spontaneous is like skiing downhill. Okay, it's the natural way. So, 2 factors that help us are enthalpy and entropy. We know a lot about enthalpy, so I'm going to review that really quick, and then we'll learn about entropy. So check it out. Enthalpy is delta H equals heat. See it again. Enthalpy, delta H, heat. All right, one more time, because that's cool. Okay, so we already know what it means. It's one of the driving forces for a chemical reaction. It's the heat content. And what's the favored condition? Like the naturally favored condition is a negative H, all right? So that's exothermic. So many exothermic reactions are spontaneous because that's the favored condition for heat. When that delta H is negative, the reaction is exothermic and the products are lower in energy, more stable. All right, so the energy content drives the reaction. Exothermic is greater stability. So many exothermic reactions are spontaneous, but not all spontaneous reactions are exothermic. Some endothermic reactions occur too spontaneously. Why? Okay, so this is where we have to introduce entropy. If the overall entropy of the system increases, even though it's endothermic, it could be spontaneous. Let's see where entropy is going to drop in. Right there. Okay. Entropy is a measure of randomness of a substance. Its symbol is S. There's a picture of the Department of Entropy. Delta S is entropy. The favored condition that promotes spontaneous reaction is one that is an increase in entropy. Right? In other words, being random is a favored condition. More random, more entropy, the better that it is. Okay, so here's an example of increased disorder. You have a solid turning to a liquid, turning to a gas. That's an example of increased randomness. Why? Because the particles have more chances of different places, different energies, like kinetic, translational, vibrational, rotational when they're gas than when they're liquid or solid. And what's more random? Gas. Okay, so looking at this picture, I want you to decide which condition has the most entropy. Check out the S's. Try one more time. Delta S is entropy is disorder. Which one of them has the most disorder? You tell me. Okay. What are some ways we can observe entropy increasing? Well, we have gases forming from liquids or solids and liquids forming from solids. All of those are increases in entropy. Okay. Solutions forming from liquids or solids. If you have that, that's an increase in entropy as well. If there's more gas particles in the products than there were in the reactants, then that's an increase in entropy. And finally, if the temperature of a substance is increased, that's an increase in entropy. Probably want to write these 4 things down for sure, and then be able to find them when we do some practice, okay? Here's a picture that explains most of what you just saw, okay? See how it relates. Look for the one that has the most different random ways to be. What has more random ways, liquid or solid? Liquid, okay? What's more random, a solute in a solvent or solution? Solution, okay? High temperature. So there's a thermodynamic law that says entropy of the universe is constantly increasing. And so if you have a messy bedroom or a messy chemistry binder, you can just say you're following the law of thermodynamics. The entropy is prevailing in your folder. But I know the trick. You have to add a lot of energy in to make it be less entropy. So do it. Anyway. So together, enthalpy and entropy predict whether a reaction is spontaneous. So increased entropy is favored. What is another way to say that? Positive delta S. And decreased enthalpy is favored. It's a naturally favored condition. Okay. So if both of those are happening in a chemical reaction or a physical change, those conditions will always promote or produce spontaneous reactions. Okay. At any temperature. So what does a spontaneous reaction do? It releases Gibbs free energy. And Gibbs free energy is free energy that is available or free to do work on another system. So say you light charcoal on fire, right? So you're increasing, or it's exothermic, giving off heat, and it's increasing disorder because the charcoal is turning into all different kinds of particles in different random ways. And so then, after that, those hot charcoal coals, where they're decreasing heat, that's exothermic, and increasing randomness, can cook a steak or a tofu burger. Okay, delta G is Gibbs free energy. All right, so here's a mathematical formula for delta G. So memorize it. If you haven't already, do it now. Write it down. Memorize it. There's 4 letters in it and 3 triangles, an equal sign and a minus sign. You do it. Okay, so delta G does predict spontaneity. If delta G is negative, the reaction is spontaneous. Negative delta G. I have a sneeze coming up. Excuse me. Whoa, sneezing in a video note. What? Okay. If delta G is positive, the reaction is not spontaneous. Because that means there's no Gibbs free energy given off. In fact, you have to add energy in to make the reaction happen. Okay. If delta G is 0, then we have what's called equilibrium. Equilibrium is where both reactions, a forward and reverse reaction, are occurring simultaneously at the same rate. Okay. And then free energy, just to redefine, is energy available to do work. All right, so, there it is, the formula you're going to memorize, mathematical formula that has all the things we're talking about in it. We'll define each thing. Delta G is Gibbs free energy, usually in kilojoules. Okay. Delta H is the heat of a reaction, kilojoules or kilojoules per mole. All right. T is temperature in Kelvin. Okay. And then delta S is disorder randomness, which is entropy, which is kilojoule per Kelvin. Okay. All of those are the little pieces in this equation that you have to know. Okay. So, hey, can we calculate? We can. Hey, a system has a temperature of 298 Kelvin. That to me looks like a T. Temperature, 298 Kelvin. Enthalpy change. Enthalpy, which one? I think it's delta H. Right? And an entropy change of, entropy, delta S. Woo. What is the Gibbs free energy? And is this a spontaneous reaction? So let's do it. Delta G equals negative 223 kilojoules minus 298 Kelvin times 0.035 kilojoule per Kelvin. What happens here? We multiply these, cancel those out, and then we multiply those together and do that. And if we do all that math, we get negative 233.43 kilojoules. All right, so now we got to decide what that means. So here's a negative sign. So delta G is negative. That means spontaneous, because this much free energy is released for this process. I don't know if you guys heard that, but my dog just ran by. So, what is the Gibbs free energy? Right there. Is it spontaneous? You bet. Yes, because that means spontaneous, negative G. Okay, so we can predict spontaneity using values for H and S. All right, so if delta H is negative, that's favored. Woo. Delta S is positive, that's favored. So yes, it's going to be spontaneous all the time. If delta H is positive, okay, so this is favored by nature. Favored by nature. This is not favored by nature. Decrease in entropy, that's not what nature wants. So is that going to be spontaneous? Nope. Nope, nope, nope. All right, what about when delta H is negative? That's exothermic. Exo. Delta S is negative. Ooh, that's a decrease in entropy. That is not favored. So one of the driving forces is favored and one is not. That means it may be spontaneous, maybe. Okay. What if the delta H is positive? Ooh, nature doesn't like that. That's endo. And entropy goes up. Nature likes that. So we've got H and S both doing the same thing, going up. One's favored, one's not. That means it may be spontaneous. So what does that mean about delta G? Well, spontaneous means negative delta G all the time. Okay, at all times. At all times. If it's not spontaneous, that means delta G is positive at all temps, and that's not spontaneous. Okay, so what if it's maybe spontaneous when the driving forces are one's favored and one's not? Calculations needed to know if delta G, and it depends on the temperature of the reaction. Okay, same thing here. All right, so for maybe spontaneous based on the S and H, then you have to do a calculation. It depends on temperature. What calculation does it depend on? It depends on this calculation. Delta G equals delta H minus T delta S. All right, that's the calculation needed because it's the temperature that's going to determine if it's spontaneous or not. So you can get negative G, spontaneous, free energy release. Positive G, non-spontaneous. You have to add free energy in to do work. When delta G is 0, the reaction will be in equilibrium. Okay, make sure you know that. If the delta G is 0, then the forward reaction going that way and the reverse reaction going that way are occurring at the same rate. So those are the conditions. When you get a maybe, this is a maybe, all right, equilibrium is possible. Okay, maybe means equilibrium is possible. We're going to spend more time talking about equilibrium. Delta G is 0 is equilibrium. But when you get, going back, when you get these conditions, that's when equilibrium is possible, when you get a maybe spontaneous. Okay, so please do read this section, write your 3 questions. Right. Here's a review. Enthalpy and entropy help determine spontaneity. Knowing how to predict delta H and delta S, whether they're increasing or decreasing, helps you predict spontaneity. Enthalpy favors negative and entropy favors positive. And then be able to calculate delta G doing this formula, mathematical. Entropy is disorder, randomness. Make sure you can tell that. Randomness. And gives free energy. When it's released, they're negative. It means spontaneous. Okay. That's it on these beautiful water-like slides. We'll see you guys soon.